Going to be lesson 2.2 on similar figures. Before we get into the lesson, please go ahead and do the two warm-up problems. This is just solving equations, and this one here, you're looking at setting up some ratios of these two triangles. But go ahead and pause your video, work through the two problems, and when you're done, go ahead and unpause. Okay, so hopefully you are done with these two problems. Let's go ahead and take a look at the solution for the first one. Here I have it worked out already. So what I did as my first step is I decided to do flipping so that I only have x terms on one side and numbers that don't have an x on the other side. So the 2x flipped over the equal sign to become negative 2x. And negative 7 flipped over the equal sign to become positive 7. The 4x and the 9 didn't change sides, right? This is still on the left, this is still on the right, so they don't change signs either. Now we'll go ahead and do our combining. Now over here we have a war. We have a positive 4x and a negative 2x. That is a war. They'll fight it out. Positives win. You'll have a 2x left over. Over here you have a positive 9 and a positive 7. That's the same signs. That's an alliance. They're going to combine together to make a bigger positive army of 16. And then for my last step, my goal is to get x by itself. So it means I have to get rid of the 2. And what we are going to do division as our last step, so we always divide by what's in front of x, and that gives us dividing by 2 to both sides. So we get x equals 8 as our final answer. Now for this problem, it says one triangle has sides 4, 10, and 12, and another triangle has sides 6, 15, and 18. So this one looks like the bigger triangle, right? Because these three numbers are definitely bigger than those. What is the ratio from big triangle to small triangle? What about small triangle to big triangle? So the ratio, we're going from 4 to 6. You could write a ratio that way, but I prefer to write it as a fraction. 4/6, and then for the middle sides, 10 over 15, and for the last sides, the big sides, 12 over 18. And if I look at these fractions can be reduced to 2/3 in every case. So they have the same ratio. Now, to get this into 2/3, we're just cutting them in half. We're dividing the top and bottom by 2. To get the 10 15ths to 2/3, you're dividing the top and bottom by 5. Remember, it's always the same number you have to multiply to reduce a fraction. So 10 divided by 5 is 2, 15 divided by 5 is 3, and the last one is divided by 6 to still get 2/3. Now, your calculator that we've been using, it does reduce fractions for you. So this fraction, this key right here where it says n over d, if you hit that, you could put like the 12 over the 18 and hit enter, and it'll reduce it down to its simplest form of a fraction, which in this case is 2/3. Now, if I had them flipped, if I had 6 over 4, and 15 over 10, and 18 over 12, then all of these fractions would wind up being 3 over 2. And so the ratio that we're looking, if you're going from big to small, I would use this, and I'm actually going to write these in a decimal form. This is actually 0.6 repeating. And actually I'm going to do 6/6 because this actually will make a little more sense if I use 2 decimals. And then this winds up being 1.5. So to kind of talk about this relationship, since this is lesson 1, I would look at this as the small triangle is 66% or about 67% the size of the original one. So however big this is, these sides are only 67% of it. Now if you go from small to big, then you would say that the big triangle is about 1.5 or 1.5 times bigger than the small triangle. Alright, let's take a look at similar figures. In order for two figures to be considered similar, they have to be the same shape, but they're different sizes. They have corresponding angles that are congruent, and they have side lengths that are proportional. The first one's fairly easy. Do they look like the same type of shape? Yeah, they look like parallelograms. So I would say the first one is definitely met. Are the angles the same? Now this 40 represents this angle in both cases. So this angle is 40 degrees. If this is 40, what would this obtuse angle be? This takes us back to the parallel lines that are cut by a transversal. We talked about the acute and obtuse angles. And if this is 40, this acute one's 40, then this obtuse is 140. And that's going to be true in both of these because of these parallel lines. These angles are supplementary. They add up to 180. And this one's 40, and this one's 140. So all these angles do match. So the second criteria is met. Now, are the sides proportional? Well, that's where you're going to take the sides, and they're all 42 and 35, right? So if I put 42 over 35, or I do 35 over 42, I'm going to get the same answer every time. And so we're going to say yes, this is proportional, because all the sides have the same ratio. Now, can this be simplified? Yes. We could divide this by 5, and that would be 7/8. So that would be the ratio. If you went from, you could flip it and do 8/7, depending on if you're going from big to small or small to big. Let's go to the next one. In this case, this obtuse angle is 125, which makes this one 55, because they are supplementary because of the parallel lines. Which means this is 125, this is 125, this is 55. So the angles do match up. Right, the corresponding angles all have the same, they are congruent, they're the same angle measure. What about the ratio of the sides? Well, what's the longest side on the big one? 18, right? And we'll put that over the longest side on the smaller figure, which is 7. And then the other side that we have left is the 12, which is the short side here, and we'll put that over the short side there. So in each case, we went from, these are the long sides, these are the short sides. These came from the big parallelogram, these came from the small one. Now, are these truly equal? I'm going to put a little question mark here. Well, 12 divided by 6 is just 2. And 18 divided by 7 is more than 2. It's actually, 2.57-ish. No, not similar. In order for these to be similar, these should be equal values. They should be equal to each other. And we can see in decimal form they do not. This is equal to 2. This is greater than that. Let's go ahead and flip the page. So for these here, once again, if this is 100, this is 80. Same type of deal that we had going on the other one. So the angles are going to match up, and they are the same type of figure. We're just looking at proportions now. So let's once again set up a proportion using the longer side. So the longer side here is 8. The longer side here is 66. So 8 over 66. And then we'll do the same thing with the shorter sides. So we'll do the 6 over 36. Now the question is, are these equal to each other? Because if they are, then we can say these are similar figures. If they're not, then they're not similar figures. That reduces to 1/6 if you divide top and bottom by 6. And this one, if I cut them in half, I get 4 over 33, and that doesn't reduce anymore. This is no. We don't have the same ratio, and we'd have to get the exact same ratio for that to be true. So we've now seen 2 of them where it was not, they are not similar figures because they don't meet the criteria of being proportional. Let's go to this one. These, the angles match up, right? Those angles are the same, those are the same, those are the same, those are the same. They gave you those markings to let you know that. Well, let's set up the proportions then. We'll start with this 18 off the top one, corresponds with this 7.2. And then we have the 20 corresponds to the 8. 18 over 72, that's redundant, I'm not doing that again. 35 over 14. Now the question is, do all of these come out to the same value? So let's go ahead and do 18 divided by 7.2. And I get 2.5. So this is equal to 2.5, or you could say 5 over 2, 5 halves. Well, what about 20 divided by 8? Also 2.5. Well, what about 35 divided by 14? Also 2.5. So we can see all of these do equal 2.5. So these two are similar figures. The answer is yes, because they meet all three criteria. Alright, let's take a look at the next one. This is the same type of deal with these 80s, and so if this acute one is 80, then this obtuse one is 100, so they add up to 180. The angles are going to be the same, because then this will be 80, this will be 100, so the angles work. Same shape. Now we have to look at proportionality. I'll do 36 over 30, and I'll compare that with 48 over 40. This is 6 over 5, and this is also 6 over 5. So I would say yes, those are similar figures, because the proportions, or the ratio of the sides, of the corresponding sides, do equal to the same value. And we'll do one more for this video. They're all 90 degrees, so all the angles are the same. It's just about the ratio of the sides. So we'll do the 30 over 35, and then we'll do, nope, I did that wrong, I apologize. I'm at 25 over 30, and we'll come to the top one here, 40 out of 48, and then we'll do the last one, 25 over 30. So those are the ratios. The question is, are they the same ratio? So let's go ahead and do our simplification. If I divide the top and bottom by 5, I get 5 over 6. If I divide both sides by 8, 40 divided by 8 is 5, and 48 divided by 8 is 6. And then the last one, 25, that is a 5, and that's a 6. So 5, 6 again, if you reduce. So we can see that the ratio of the sides is the same. Remember, it must be the same sides that you're making that fraction from, and you need to be consistent. If you're going to put the bigger number in the top, or the smaller number in the top, you need to do that all 3 times when you're comparing those. Alright, I'm going to go ahead and finish this part 1 of the lesson. So if you would continue to go on to part 2.